Okay. Hello, my name is Jeff Eidem, and welcome back to Khan Academy. Now, of course, this isn't actually Khan Academy, because if it was Khan Academy, it'd be much better, much higher quality. And if you actually struggle with this problem, if you actually struggle with understanding electron configurations, which is what we're talking about in this video, then I recommend that you go ahead and watch a Khan Academy video, because it's going to be much more beneficial to your learning and help you to understand much better. So like I said, today we're going to be talking about electron configurations. So what does that actually mean? Electron configurations, what that means is talking about a set of orbitals occupied by the electrons of a particular atom or ion. So to do that, so basically what that means is it's talking about in which orbital are the electrons of a specific atom. Where are they? What are they actually doing, right? To do that, we're going to talk about what's first called SPDF notation. Now, for SPDF notation, we're going to use hydrogen for an example. All right. So for hydrogen, that is going to reside in the s orbital, right? And on the first shell, so it would be 1s, and then you're going to write how many electrons are in there, right? So for hydrogen, there's 1. Now, for future reference, we're going to need this a little bit later, but this right here, the 1, that is equal to the value of n, right? So that comes from our quantum numbers, which we learned in the previous lesson. So yeah, that is the n value. So the s value, now that is going to equal the value of, and that also comes from our quantum numbers. Now this third number up here, this one right here, is going to be one of the really important ones. This is going to equal the number of electrons that are in that that specific atom that we're talking about. Now, once we have this is really important. You're going to need to remember this. But when we have the second way of writing these is we're going to be writing these in the orbital diagram notation. And what that is, that looks like this: orbital diagram notation. Okay, and so now what that looks like, now instead of it writing it like this, how we had it previously, so we had it written like this for hydrogen. So this is for hydrogen, right? Now, instead of writing it like this, how we're going to write it, they're going to be written in boxes. So I'll do that. I have a little box, right? And this is going to be the 1s box. And there is going to be, for hydrogen, of course, there's only going to be 1 electron. Now, each one of these boxes can hold up to 2 different electrons. So this is for hydrogen, right? But if I were to do this for helium, now this is going to be like this. It's also going to be it's going to be 1s, but instead of having only 1 electron, it's going to have 2 electrons. That's going to be represented by 2 arrows, just like that. Now, as we keep going, as we get bigger and bigger, we're gonna actually go back to the electron configuration. Well, I guess this is both electron configuration, isn't it? And so what we're going to talk about now is how this looks like for different kinds of elements. So for example, if we do lithium, so lithium has a total of, so we're going to write it in the notation, in the previous, in the SPDF notation. Lithium is 2, right? It's 2, and it has, well, meaning that it's in the 2s orbital, and it has how many? It has 3 electrons. So what is that? What's that telling us? That's telling us that we're going to start, and it has 3 electrons, and it's going to continue in order. So first, it's going to go the 1s orbital. It's going to have 2, right? and that would be helium. If I had just left it just like that, it'd be helium, right? But I'm going to continue it. I'm going to go to the 2s orbital now, and that's going to have 1 electron. So that's how we get this, right? So this is basically, this right here is basically the ending state. That's going to be represented by this right here. And now let's continue with a few more examples, right? So we have carbon. So carbon is going to be in the 2p. I guess writing like this really isn't the best way to write it in this, because, well, let's just continue. So let's talk about carbon. Now, carbon is going to be in the 2p orbital is where it's going to finish, right? So we're going to start out, we're going to go in order. It's going to be the 1s, and there's going to be 2 electrons. So total, it has how many? It has 6 electrons. So it's going to be 1s, and then it's going to go to the 2s, and in 2, there's going to be 2 and 2s, right? Because each s orbital holds 2. And then now that it's leaving the s orbital, it's going to go to the p orbitals. So it's going to the 2p orbital, and now there are 2 electrons within the p orbital. So that means it's going to be 2. And like I said, this has 6 electrons total. And so if you add these up, it's going to equal 6. Okay. A couple more examples. Let's go with neon. Now, neon is a I'm forgetting what you call it. It has 8 valence electrons. I mean, that has the full octet, right? And so let's talk about what that means. And so you're going to start with 1s, right? And then you have 2s, 2, and then you have, how many do you have in the p orbital? Now you have 2 in the 2p, and there's going to be 6. So now there should be 10. 10 electrons total. And if we look at a periodic table, we're going to find that neon has 10 electrons. Now going back, our final one, we're going to do a little bit of a longer one now. Now let's do, how about, let me see, how about, I think it's, let me pull my periodic table, sorry. Perfect, okay. So for now, we're gonna do one that's a little bit longer. Let's maybe use, perfect, yeah. Let's do Br or bromine. So bromine, yeah. So bromine, how many total electrons does bromine have? Bromine has 35 electrons. You know that because on the periodic table, the little number above it is 35, right? So what we're gonna do, we're just gonna go in order. We're gonna go first 1s, and there's gonna be 2 there, and then there's gonna be 2s, there's 2 there, and then it's gonna be 2p, right? We're gonna continue, and there's 6 there. So now we should be at equally neon. And if we leave it here, it's just like neon. But we're gonna keep going, and now we're going to 3s. And the 3s, we have 2 more, and in the 3p, we have 6 more. And then after 3p, we go to the 4s, which has 2 because all the s orbitals hold 2, followed by the 3. Now this is where it gets tricky. We need to remember, just like in his slides, he has a really good figure that shows this. Oh, perfect, right here. So it doesn't always go, once we get to about this point, once we get to this point, I'll get a better color here so you can kind of see it. Once we get to right here, we see that the 4s actually, we're getting to where we have a 3d orbital. And because 3d is actually of a higher energy than 4s, it's going to get filled after the 4s. So we're going to go 3p to 4s to 3d. Okay, so now if we come back here, after we have 4s, we're going to go to 3. Oh, let's go back, keep it consistent. You know what I'm saying? We have a 3d orbital. Now the 3d orbital holds 10, and then we have a 4p5, just like that. So that's going to be the written electron configuration for bromine. Now, if we add all these up, it should equal 2 plus 2 plus 6, that's 10. 10 plus 2, that's it's 12. 12 plus 6 is 18. 18 plus 2 is 10. 10 plus 10 is 30, and 30 plus 5 is 35. Exactly what we said we should have, right? So now that's how you do the written electron configuration for these, right? Now, every once in a while, well, when you get some of these are getting like, this one's getting pretty long, you know, to have 35, you know, but there is a shorter way to do it. So instead of writing this whole big long equation, we know that argon, that it's going to be the exact same up until argon. So what I mean by that is, if say this was a 4, say instead of a 5, that was a 4. So now, instead of talking about bromine, we're talking about celium, right? Celium. But up until argon on the periodic table, or what would be 3ps, up until right here, right? These are all going to be the same. It's going to be same to right here for all of these until we get to another noble gas. So until we get to krypton, which would be 3p6, all of these are going to be the same. So we can write an abbreviation. And what that means, so let's imagine we're writing krypton. All right, krypton. Instead of writing all of these, we can just write AR, put in brackets just like this, right, for argon, because it's going to be the exact same up until argon. And then we'll just finish from there. We're going to go 4s2, we're going to do 3d10, and then we're going to have a 4p6, and this is going to be krypton. Now, if we add these up, this is up until this point right here. I guess it's better to do that. You know, we're going to have 2, 4, 10, 12, 18. So argon has 18. So this is, we're going to stop here. And so we're just going to write argon in brackets, showing that it's going to be the same up to argon and then the right after argon. And to abbreviate, you always just put the noble gas that comes before it. You're never going to put another atom or another element that's not a noble gas. So you never use fluorine or never use phosphorus or aluminum. It's always going to be helium, neon, argon, krypton, xenon, and radon. Okay. Now, going back to how we were previously talking, that's kind of how you do the written form. Now we're going to talk about this form right here, the orbital diagram notation. So each one of these boxes is going to be able to hold up to 2 electrons, right? So let's talk about nitrogen. So nitrogen has 7 electrons. So this is going to be the 1s, and this is going to be the 2s, and these ones are all going to be 2p's, right? And 2p's, and because total in the p orbital, they can hold 6 electrons, right? So 2 each. You have 2. Oh, you have 2, 2, 2. Okay. So for nitrogen, we're gonna have 1 in the no, sorry, 2. We're gonna have 2 in the 1s. We're gonna have 2 in the 2s, right? And then in the 2p, we're gonna have a total of 3 in here. Now, this is an interesting rule because it's going to be really tempting to go do something like this. Do 1, and then a 2, and then a 3. But this is wrong. Don't do that. The correct way to write these is actually, you're going to put 1 in each box until they're full. So you're going to be 1, and then 1, and a 1. And this is going to be how you write for nitrogen. And that the reason for that is the electrons, because they have the same, I guess, the same, well, they're the same, so they're going to be repelling from each other, right? So the electrons are going to want to get as far apart from each other as possible. And so because of that, they're going to spread into these different orbitals before sharing. Now, if we continue and we have like, so for example, we have oxygen. Oxygen has a total of 8. And so then we're going to go back and put the 8th in here. And for fluorine, we're going to put the 9th in here. And for neon, we're going to put the 10th in here, okay? If that makes sense. So I hope you guys are able to catch on to that pretty well. I feel like it's pretty straightforward, and you should be able to get a pretty good understanding of that. So next, what I want to talk about, let's move on. So next, what I want to talk about, I want to switch gears just a little bit. I want to talk about nodes. So the nodes in orbitals, just like this, okay? Now, before we were kind of talking about the written way to see electrons and where they are, but now we're going to kind of talk about in the real life where the electrons actually are within, like where they are and how they sit inside the different orbitals. Now, we have a couple different kinds of orbitals. We have the S orbital, we have the P orbital, we have the D orbital, and we have the F orbital. And you guys already know that, right? So we're going to talk about nodes. So what is a node exactly? A node is a region that there is zero. I'll write this down. Region with zero, just to emphasize, probability of being. So it's where there is no chance that you're going to have an electron of being. Now, to begin with the S orbital, well, actually, and there are two kinds of nodes. The first is going to be a planar node. And the second is going to be a radial. So what do those look like? A planar node, for example, and we'll get into this more, is going to be, if you think about a P orbital, a P orbital is going to have one planar node, meaning that it is dividing it in the middle, and there's almost like separate lobes of where, and the electron can be found anywhere inside of these right here. But all of this area out here, there will never be an electron found out there. And that is going to be a planar node. Now, radial node are really only found in S orbitals. And if this is your element or your atom right in the middle, a planar node is just a spherical, it's just like that. And the spherical node is found on the outside of these. So the electron can be found anywhere inside of these. Now, if we have two, for example, for example, a 2s, it's going to have two of these. Now, there is going to be, where this line is right here, that line right there represents where there's going to be zero probability of finding electrons. They'll be found out here, and they'll be found inside, but in between, they'll never be found. And between the next one, if I go like that, every line here, every line, okay, this is weird. Okay, every line right here, and right here, each one of those lines represents where you're never going to be able to find electrons. Now, how do you find out how many nodes are actually within how many nodes you actually have, right? So what you're going to do is you're going to take the n, and n is equal to the shell. So if we're talking about for example, sodium. So sodium is in the 3s. So sodium has a 3s. Oh man, what's going on? 3s1 notation, which is what we get from up here from the SPDF notation. Now, what that means is this is equal to n, like I was saying before. This is not equal to n, that is equal to the L, and this is equal to the n. And n, and to find how many nodes, you're going to take n minus 1. Okay, and that is going to tell you how many total nodes you have. So n minus 1, so I have 3 minus 1. That means you're going to have a total of 2 nodes. So sodium is going to look something like this. It's going to have one circle with that, and it's going to have a second circle wrapped around, just like that. And so there's going to be one node here and one node here, if that makes sense. I guess a better way to look at it would be like, if you look at it like this. And so if you're imagining that there can be something here, an electron here, and there can be an electron here. So the nodes be between right here and right here. Those would be your 2 nodes. And then to find out how, and that's how many, and for in this case, that's how many spherical nodes, right? But if we look at something like, if we look at a molecule like carbon, so carbon is C, it's going to have a 2, well, it's going to be written like this, 2s6, okay? Oh, I apologize, that is not going to be written like that at all. It's actually going to be written as a 2p6, right? So what that means, you're going to have your total number of nodes is going to be n minus 1 equals 1 node, okay? And so it has 1 node total. And so how do you, this isn't going to have a spherical node, a radial node, because it's not a sphere, right? Because it's in the p orbital and it looks like something like this. So what it's going to do is you need to find the planar nodes. How do you find the planar nodes? So the planar nodes is going to be, let me just pull this up. So planar nodes is going to be n minus 1 minus, well, I guess an easier way to be would be to show how to find the radial nodes. So let me just bag all this, okay? So first, you're gonna find the L, you're gonna be looking for how many planar nodes, all right? And the planar nodes, you find that by, just make sure I'm not confusing you guys. Right, that's equal to your L value. So your L value, okay, so if I'm looking at carbon, right, I'm gonna have a 2p, 2p, what, 2p2? Yeah, make sure I'm doing that right. Yeah, carbon's 2p2. So what that means is we're gonna have, this is equal to your L value. And your L values are S is equal to 0, your P is equal to 1, and your D is equal to 2, and your F is equal to 3. So L is equal to the number of planar nodes. So how many nodes is carbon going to have? It's just going to have 1. It's going to be right here. Just like this, there can be electrons here, and there can be electrons here. And then if to find your number of radial nodes is what you're going to do is you're going to take your total number, so n, and you're going to subtract 1, which is going to give you your total. And then for total, you're going to subtract your L, and that is going to equal to the number of radial nodes. And what that kind of looks like if I'm doing something like, find a good example. Yeah, so let's get, for example, if we're talking about potassium. So potassium is a 4s1. So this is going to be equal to my N. This is equal to my L. And so I'm going to take N, which is 4. So I'll just delete that. So we have 4 minus 1. So that is equal to my total number of nodes, so I have 3. I'm going to take 3 minus my L. Now my L here is equal to S, and S is equal to 0. So that is 0. So I'm going to have 3 radial nodes. Okay, guys. Well, I hope that this has been at least somewhat beneficial. Like I said, I'm really, I'm not a pro at this stuff. So if you're really struggling with this, you should probably go watch like a Khan Academy video because they're going to explain it much better. And I hope you guys do well on the final. All right, bye.